Good morning, everyone. Sorry, I'm going to use my loud projective voice. I probably should get started since I have I was just saying I have a crazy number of slides, which will be like a long pecha kucha. So for those of you who don't know me, I'm Isla Berman. And today I'm going to present an overview of our book, myself and Andrew Kudless, our book Flux, Architecture in a Parametric Landscape, which is a kind of theoretical overview of the impact of computational and digital technologies on architecture and its radical evolution over the last 25 years. And in the book, we focus on the relationship between encoded matter and digital craft. Now, one of the main arguments of the book is that since the mid-1990s, digital technologies have really catalyzed one of the most creative and prolific periods in architecture since the early 20th century. That's one of my main arguments. And although this, through this evolution, we moved from tools that started out being highly representational to eventually those that were capable of entirely transforming the ways in which we conceive and configure form, space, and material. I also argue in the book that there is no such thing as a parametric style, Patrick Schumacher, sorry, or computational style, but instead that the kind of diversity of designed architectures and objects that we produce using computation are a reflection of the complexity of the advancing tools, their logics, and the systems that we're using, whose evolution is continuously breeding new types, right? And these are unlike our previous ways of thinking about typology, and instead, because of their relationship to code, are closer to a kind of infinite diversity of architectural species that share some common genetic traits, which I'm going to talk about today. So if the capacity for variation was one of the standard tropes of the digital revolution, in opposition to what was the repetitive sameness and standardization of modern industrial production, then it is precisely this variation that is also one of the key characteristics of the architectures generated using computational tools. Variability for us is also, I would say, a deeply rooted ambition of architects and designers in general, in the sense that uniqueness is intrinsic to the idea of creativity and to authorship, and also to matter and form, where its emergence is always specific to a history and to a specific environmental context. Now, just to give you a bit of history about this project, Flux began as a research project many years ago. This is probably the longest book I've ever done, with an installation and exhibition that Andrew Kudless and I did at CCA, California College of the Arts in San Francisco, in concert with the Smart Geometries Conference of 2009. And the installation that we did and exhibition, so it was both an installation and exhibition, the installation that supported the exhibition was an embodiment of the ideas of the exhibition. It was a twisted, tubular, parametrically designed armature that was defined by a hexagonal cross-section that had these ribs that held planar elements, and these planar elements were canted for viewing, and that's what supported the exhibition content. And the content was originally organized, this was one of the posters that we did for the exhibition. It was organized through 8 thematic categories, each of which explored a set of formal and spatial logics that have been transformed through computational practices. And then a few years later, this is the table of contents of the book. Here, I'll pass around the book. You guys can look at it. So a few years later, we decided to extend the work of the exhibition and expand both its contents and the analysis into a book. And we decided to retain the original taxonomy of the 8 themes, but expanded the research so that it would track their evolution over time. And the works chosen, it's not comprehensive. They're considered to be sort of seminal examples that stand in for a larger group of artifacts that aren't included in the book. So the book theorizes and analyzes over 140 projects developed by a range of designers, and they come generally from three groups: smaller experimental practices, large firms that often had sort of research arms that were part of the firms, and advanced academic institutional research groups like the DFAB Lab or the Block Research Group at the ETH in Zurich. And I'm going to present a cross-section of these today. And just to give you an idea of how the logic of the book works, so we had 8 themes. So there's 8 sections of the book, and each of these sections has 3 key segments. This is a kind of quick synopsis or an extract from 2 different sort of chapters. So there's and each one starts with this kind of wallpaper graphic that we designed for the section. So each one has 3 sections. The first is a theoretical analysis of the topic and its formal and material logics. The second is a project section that is somewhat, it's thematic and somewhat chronological, but we always start with a historical example that is often not a computational project, but that's about the kind of logic of the project. And the third is the kind of generative analysis section that explores the mathematical and generative logics and processes of a selection of work. Now, for us, drawings and models are familiar tools that we always use to probe and analyze architectural works. And here, the analysis occurs on the one hand through a set of theoretical concepts and mathematical concepts and geometrical concepts, and the creation of parametrically encoded models that reveal a kind of set of procedures that we use to analyze, but also to regenerate sort of each project. So the models were created, they didn't come from the architects, and that also were intended to extend the potential of those projects by revealing how a change in its potential inputs, its variables, would translate into incremental changes in a customized output or design. Now, while we, just so you understand sort of how we worked, while we curated all of the projects together and decided, and the themes, Andrew and I did all the writing for the book, the theoretical analyses and the project sections. Andrew did all the scripting for the generative analysis section. And the purpose of the analyses of these works is to expose what I call the kind of hidden virtual envelope that surrounds every parametrically generated project, which, akin to a game, if we think of how games operate, might include not just the rules of interaction of the game, but also the plurality of all possible plays that these rules might enable, right? So a unique artifact that contains, in a way, a genetically coded framework is always able to generate multiple siblings. I often say in architecture, we don't design projects, we actually design machines that create projects. And this is even more true with, because of the digital world. And we're making decisions all the time in relation to what those inputs are. And because each project sort of has the absent sort of related siblings, it transforms our ideas of what might constitute a prototype. Literally, proto is before, type is a type, typology, what a prototype means within design. So I'm going to run through all 8 sections of the book very quickly, so that we start with stacked aggregates. And we start with stacked aggregates because architecture is largely made up of the addition of incremental parts that aggregate into larger assemblies. It's like the most sort of primitive understanding of architecture. The most archaic forms of building are dependent on the simple accumulation of material. And in principle, the aggregative system begins with the repetition of the found or the mass-produced, given that we are in a post-industrial age, the mass-produced ready-made unit, which, because of industrial production, each unit is often the same form, the same shape, right? The same material, the same scale as its neighbor, and it is dependent on proximity, friction, and its load-bearing capacity to ensure the structural stability of the whole. With the introduction of computation, However, two fundamental changes occur in our understanding of stacked aggregates. The first is that we now reconceive the wall as a digital surface, where the repetitive element, the brick, the block, etc., is reconceived as an array of incremental units that can be coordinated and described by numeric information. Just like the pixelated field of the computer screen of any image that's varied in tone corresponds to a precise matrix of a discrete levels of gray, right? You know, everyone is numeric, etc. The second shift occurred through the encoding of the wall that now acts like a digital surface that can be deformed by any form of information, programmatic information, environmental forces, etc. So this is the logic of the walls, for example, of the Gentenbein winery. This was by an early project by Gramazio and Kohler, that literally transcodes a kind of simulated image of a basket of grapes that they created to kind of signify the winery, right? Into movements where grays, different tones of grays, translate into rotations or translations, literally rotating the bricks or shifting them to make the walls of the winery permeable. And when you look at the image, you see the digital image on the one hand still of that basket of grapes, right? That becomes the sign of the winery. But now it's aerated to let air move through the space where the fermentation happens. In Casa La Roca by Afesta, which was Nada's and Monica Ponce de Leon's previous firm, the wall transforms from a solid boundary into a permeable screen through the incremental spacing and rotating of the blocks to register the emergence of an outdoor courtyard. So they literally, you know, make the wall as if it's a curtain being pulled back and opened up. In their Tongcheng Art Center, the wall gets pushed back to become an opening for a door, right? Well, above it, it's stretched to become porous and let light in. So we could say two distinct functional typologies, right? A door and a window get both absorbed into the variability of this single material system. And in the Max Planck Institute, which is the image on the left, the variability of the brick acts as an acoustic device to diffuse sound, right? Each case, it's a different program. Now, this logic gets applied to any homogeneous stacked material system. So not just blocks or bricks. Here, it's the wood timbers in the Westfast Pavilion. They slide outward, right? They're the same size. They slide outward to create an illuminated roofscape. Or in this project, the Mantra Hukaden, it's identical. All the elements are the same size, exactly the same dimension, the same length. They are identical stacked and interwoven timbers, where the form of the work as a whole is the result of incremental variations in the mode of assembly, rather than changing the form of individual elements, right? One element. These works, we could say then, they're consistent, they're monolithic, where quantity and its degrees of differentiation are the generators of the quality of the work. And this project uses, and you can see from the sort of diagram, what it uses is a circular fixed length chain of identical units. And as the diameter of the base gets smaller as it moves upwards, and it also rotates, the units, the timbers themselves, rotate inwards, right? Same length, right? They're just changing their position. They rotate inwards toward the circle center. And the changing of these parameters, with every generative analysis page, we talk about the generative logic, what the logic is, what the process of making it is, and then produce a generative matrix that shows what happens if you change any one of these parameters. You change the size of the timber, you change the form of the base to not be circular but square, etc., but still using the same logic. And then the last three projects in this series, we move away from the homogeneous brick or block toward the use of robotics and its ability to precisely cut and customize individuated elements to generate a kind of monolithic whole that displaces the reading of the element, the aggregation of the elements. So here it's the whole rather than the part that's dominant. This is a project by Howler and Yoon in Boston, the Collier Memorial. Philippe Bloch did the actual structural work. He actually came when I was dean here and did a lecture and talked about this project. The last project in this series is called Rock Print. It's a large-scale aggregate of gravel and string. That's it, only gravel and string that emulates a kind of full-scale 3D printed form. Now, it's comprised of alternating compacted layers of rock and string, and it exploits, on the one hand, the compressive strength of the gravel and the tensile strength of the string. But rather than using formwork that gets filled with a liquid or a kind of synthetic powder that cures and hardens and creates an irreversible process, the robotically laid string, and it's laid in these very precise, that's the pattern of the string on the right, is used as a binding agent whose precise patterning interlaced with the gravel is what is responsible for maintaining the configuration of the structure. And because, unlike 3D printing, the return to the original raw material enables the structure to be fully reversible with one pull of the string. They did this like a performing arts piece at the end. They literally, after this whole thing was done, pulled the string and it just dissolved and went back to being a pile of rock and a pile of string. The second section is called modular assemblages. So each of the sections is related to the one that preceded it in some way. Now, this second group, these are assemblies that are composed of a family of interrelated elements. So they're a study in the relationship between part and whole, because the module is always simultaneously a part and a whole. It's a fractional component of the parent from which it was derived, while also being an independent entity that can be rearranged within any closed system. Now, as a kind of simple example of this, in principle, one of the key logics of modular systems, think Le Corbusier's modular was all about dividing the body into these components. The rules are first divide, then recombine, right? That's it. So this is the strategy of Gramazio and Kohler's resolution wall, whose smaller units are all either 1/2 or 1/4 of the dimension of the larger concrete block, so that any aggregation of those components can fill the plane. This is also the logic, this was our sort of historic example that defines the facade of the Free University in Berlin, where two different module widths are used, and they have to be related dimensionally, right? With several sub-panel heights. Each of these subpanels gets further categorized into different material physical attributes like transparency or opacity or operability or depth, right? So there were multiple parameters, and these all for the university correspond to different programmatic requirements that are happening behind the wall, right? Behind the facade, so that the facade becomes a reflection of those parameters. Now, modular systems are always determined by relationships between elements, and because of this, they can take any form whatsoever, right? It's not the form that determines them. This is the facade of the Ravensbourne School by Foreign Office Architects, where they used a modular system of non-periodic tessellated aluminum tile to clad the project. And here, these are just 3 differently colored and shaped tiles that are interrelated by a single dimension. All the sides of the pentagons and triangular tiles are the same dimension, and the relationship of the angles. So 2 relationships, right? Length of the side, length of the interior angles, and this enables composites of the aggregation to fill the plane. In Moss's Ivy coat hook system, right? So this is a coat hook system. The system's pattern of growth, the whole idea was that you can place this on a wall, you can have any number of elements, right? They're all determined by local connections, but it allows the artifact to grow over any wall or surface. And like the Bloom game, And this was a game that was sort of set up in a park where kids would interconnect these modules. The modules can be assembled without extrinsic limits on their quantity or placement, despite having very specific limits on how they locally connect with each other. What's important here are the rules of connection. So in architectural models, we could say those external limits might be given by site constraints, programmatic demands or desires, all of which in some way are external to the modular system. Now, the opposite of the Ivy coat hook system and Bloom game, which I refer to as sort of extensive modular systems that start with the local connection and work outward. Emerging Objects, which is Ron Rael and Virginia Sanfratello, their project Seat Slug is also a modular system using a high degree of customization, both at the level of the configuration of the larger object and also of the component part. And its high degree of surface articulation is the thing that actually hides, like Bloom game. You know, Bloom game, it's so the element is so complex that it hides sort of its modularity. And in the case of Seat Slug, so this is the module, right? This is the module, that's the tile. And what's important is only these moments of connection, right? Because those are the dimensions that become important. Anything can happen on that interior, and the more complex that interior is, the more the module disappears, and it's based on the Truchet tiles, right? If you look at the bottom, the second image, for example, in the Truchet tiles, you know, the surface of the Seat Slug is a repetitive pattern of meandering lines and amoeba-shaped perforations that, like the Truchet tiles, whose continuous surface pattern hides, as I said, the legibility of the grid of the tiles below. There's one more thing that they do, and that you can see in the last sort of image that we did of the tiles, is that then they warp those tiles, right, to produce the Seat Slugs. They start with the grid, it's a modular grid, but then they warp it to form the sort of Seat Slug. And because of this, every tile only fits in one spot, right? Because of the warping and the manipulation of the form, right? So like the Bloom game, as I said, it's the complexity of the element that hides its or surface pattern that hides its modularity. But it is, well, the first one is infinitely extendable. This one is defined and closed. Now, finally, modular systems are entirely scaleless, right? Gilles Retson, who's at the Bartlett in London, he reduces the number of component types, and this calls attention to the discrete part and its relationship to other parts in the system, eventually scaling up so that the module literally becomes a part of a room, right? Can be a surface tile, can be a piece of a room that gets aggregated for housing through their automated architecture lab at the Bartlett. In pixelated fields, we look at the shift that occurs from framing, the framing of modern architecture, to the fill, or from object to field. And the field, the pixelated field, territorializes space not through boundaries or structures, but through occupation, scattering, and distribution. The KIT workshop by Junya Ishigami, here the pixelated field is the changing distribution and density of 305 slender white steel columns that fill the space. And the bottom image on the right-hand corner here is the actual, is looking at the plan of the field of these columns. So what changes is the dimensions of the columns, their rotation, and then their position in space. Those are the three things that are their parameters. And here, space isn't defined by walls or rooms, but instead by the changing density of the field. A cloud of points in plan and ethereal lines in elevation. They wanted them to be so thin, right, and white, so they would almost sort of disappear. And it produces these forms of fuzzy zones of occupation. And I should note that, and you can see from that image, that the way they organize the furniture was also, right, as a field, like clusters of desks that become these sort of clouds. Now, the potential of the pixelated field was exhibited early on in the de Young Museum by Herzog and Demeron, where they used a digitally filtered image of cloud or of tree canopies in Golden Gate Park. The museum is in the park, as a way of reinterpreting context, and use that to produce, from that image to produce what became a perforated copper skin, right? Where the changing distribution of the holes, which change in size, let more or less light in through the skin. And one of the most iconic examples that we all know of an architectural bitmap surface is the Agbar Tower project that uses a pixelated diagram to conflate multiple images in the making of its building envelope, which is a kind of reference to the polychromatic Catalan facades in Barcelona. And they take two images, the image of a geyser erupting and a pixelated mapping of the urban environment surrounding the Agbar Tower that they then fold back. They conflate these two images, fold them back onto the skin. And then that pixelated image on the one hand becomes the openings in the structure. It's literally a concrete tube that's got these punch pixelated openings that are then layered with metal panels and louvers, where the color of the panels were part coming from the geyser, the mountains, and the sea and the sky, right? And this produces this sort of pixelated layered surface. Now, the expansion of the 2D pixelated surface into 3 dimensions generates what we call volume elements, or voxel. Voxel is short for volume element, just like pixel is short for picture elements, right? So the 2D square becomes the 3D volume, and these become atomized components of volume that act like a 3D datascape of the changing parameters that might influence the design. So these are 2 projects led by MVRDV. This one is built, the Sky Village project in Copenhagen. And here the cubic pixel becomes a variable that might refer to the minimal amount of space required to support a housing unit, right? So it's a unit or an office space whose position and orientation and distribution are based on the statistical desires of the whole. So they step it back so that the roofs of the pixels become terraces. They orient it to let light in. They carve it at the bottom so that it becomes an entry, etc. And here, the atomization of space enacts a kind of 3-dimensional digitization of all programmatic requirements, so that these can be responded to through the addition, the erasure, the scaling, or redistribution of voxels, or the changing geometry in the building envelope, which is what the generative matrix looks at, both the kind of envelope, but also its erosion, etc. And in the porous city, or porosity, this was a project that Vinnie Mas led in the Y2 factory at Delft that became an exhibition at the Venice Biennale. Here, the voxelated field is both, it equates solid and void pixels, or voxels, to enable the injection of public exterior space and light and air into the verticality of the dense skyscraper without increasing its volume, right? Like, it's all about, even though they built these originally with white Legos, it was all about thinking about public space, thinking about light and air, without, increasing, for the limits became the limits of the skyscraper. And in the last project I'm going to show you, the computational chair project, this was a project by EasyCT, which is Philippe Morel. The voxel stands in for literally a bit of matter needed to withstand the load of a sitting body that is progressively eroded from an initial simplified chair. They took that, right? The idea of a chair, they divided it into a grid, spatial grid of voxels, and then they developed an automated computational process that was intended to find the lightest chair constituted by the smallest number of voxels. They sort of gave up authorship, wrote the program for it, and let it sort of determine it. Now, what's sort of fascinating about this is it moves outside of our idea of chair, right? Because it's just producing based on these parameters. So it's evolving a population of chairs whose expression of the voxelated field is a kind of continual reminder of the digitized spatial model upon which it depends, right? Because you can determine the resolution of this, right? So by intentionally still being able to see the kind of voxel, it's about retaining its logic in the final form. Cellular clusters, in the section cellular clusters, we now mark a kind of clear departure from the orthogonality of modern models and explore the overlay between computational and biotic systems, because cells, bubbles, crystals, honeycombs are the basic elements of biological models, chemical models, geological, spatial models. And of course, this is an extension of the renewed interest. So this was our historical example, was Buckminster Fuller's geodesic domes. You know, the renewed interest in polyhedra that came back, and the cellular architectural experiments that come out of the 1960s and 70s, which, like the metabolists in Japan, look to biotic systems and their structures for architectural inspiration. So the reemergence of cellular architectures was influenced technologically by the introduction of digital tools like Voronoi generators. Everybody remembers the Voronoi generators, and automated processes of tessellation that divide and pattern surfaces and volumes according to what we call the opportunistic occupation of space, like those that were used in Heatherwick's studio to determine the patterning of cellular concrete enclosures that end up getting filled with earth, that start as piers and then become these cellular structures, that produces this raised artificial landscape of Little Island by Heatherwick's studio. Cellular systems are either additive or divisible systems. They can be both. They are always made up of discrete components, modular phenomenon, that are determined by local rather than global ordering parameters. And they still operate at the scale of the whole by distributing forces in a nonlinear way. Now, cellular systems can be loosely formed or highly regular. They can have different degrees of porosity. This is the Vusor Cloud project by Iwamoto Scott. But they are essentially repetitive systems that evolve through packing, filling, or tiling strategies. The shape of the cell is also differentiated from the larger global form it supports. And this is evident in early projects by Aranda Lash, their quasi-table and fauteuil chairs, where the form of the table or chair is entirely distinct, right, from the geometry of the cells of which it was made. In the same way that the form of our bodies is entirely distinct from the shape of the cells that make us up. And if I wanted to become a quasi-table, my cells would just get really big so that I would start to become lumpy and you would understand what I was made of, right? Or in projects like the Water Cube in Beijing, which is a volumetric cellular cluster that derives its structure from the suspended state of a foaming liquid, a cube of water. And they did that because it was housing an aquatic program for the Olympics. But here again, the structure of the building, you know, is a rectilinear form, which is entirely distinct from the structure, the aggregate of which it's made. And it's made of a repeating aggregation of two kinds of irregular polyhedral cells of equal volume that actually were highly structured. You can see on the right, but they rotated them 60 degrees so that the cube would actually slice the surface, so that the elevations that would be revealed by the slicing of those packed cells would appear intentionally to be more erratic, because they were trying to reference nature's ability to conceal the geometric coding of its cells and bubbles behind the irregularity of its appearance, right? Now, these cellular structures can be derived from different origins. In the case of the 2011 ICD-ITKE Pavilion in Stuttgart, they used the sea urchin's plate skeleton morphology as the kind of study, to develop the structure. This is a project by Andrew Kudless, the Confluence Park Pavilion in Texas. Here, it's also a Voronoi series of cells that produces the triangular petal, right? Each of these is a cell structure when you see it sort of flattened in plan, but it produces a petal pattern of shells. So cellular structures can be used for structures, surfaces, spaces, etc. And this is the last project I'll show you from Cellular Morphologies. This is a CAPSARC project by Zaha Hadid, where a hexagonal prismatic honeycomb structure is used to organize their courtyard morphology that locally responds to sunlight and wind and heat mitigation in a desert landscape. So the form of it is continuously being modulated. Serial iterations of the grid and the assembly line was perhaps one of the most dominant models of modern thought, engendering a kind of new mechanistic and cinematic world that was based on the idea that both space and time were homogeneous and infinitely divisible. And that serial structures, we could say, are still really pervasive, right? In the Fab Lab, in so many contemporary works, from the serial splines of computer models to the tool paths, right, to the print layers that you see in 3D printed models, so 3D printers, CNC millers, et cetera. And this, in a way, is evident that the technologies and the practices that they have spawned are less a break with modern history than the outcome of its dynamic evolution over time. The key transformations to the way to think about seriality that occurred, its changes through computation, resulted from what I call 4 related phenomena. The first was the introduction of algorithmic differentiation into the repetition of serial elements to produce variation while maintaining continuity. I always say rhythm is repetition plus difference, right? And here we have differentiation, but it's algorithmic differentiation, smooth differentiation through the repetition of serial elements. The second is the ability to model complex curvilinear surfaces and volumes with a high degree of precision. Then the shift from strategies of framing to filling space, made possible by the ever-decreasing size of the increment. And lastly, the ability to compute enormous quantities of data and prototype at extremely high speeds. This is what computation allows us, right? Huge amounts of data, incredibly fast speeds. And this was made explicit in Michael Hansmeyer's subdivided columns project, where 6 million faces of an intricate 3D model, right? A 3D model that is has faces, are serially intersected with horizontally stacked planes that he then translates into 1 millimeter thick CNC milled ABS sheets that are then stacked, right? These are made up of 1 millimeter thick sheets, right? That are stacked. So it's the issue of quantity, right? Like this incredible quantity, so we can produce the articulation, and the point was that the surface would be incredibly complex to show just what sheer quantity and speed can do. Seriality also enabled us to exploit and redeploy existing industrial sheet materials in new ways, right? Because we've already turned the world into a 4x8 sheet of anything, right? Glass, metal, perforated, wood, plywood, etc. So now we use that, right, but rethink it. And this is what happened in the Rip Curl Canyon project by Bal Nohes, where they construct a synthetic landscape. It's made out of only 5 different profiles, 5 different types of profile. It's all made from ready-made corrugated cardboard sheets that undergo only two different transformations, shifting up and down and rotating in space, right? That's it. So vertical translations and rotations that, if they are proximate enough and numerous enough, produce this curved surface in space, right? It's not, they're stepped, right? But because of the scale and because, and as I said, it's a repetitive set and a very small set, but it produces what seems to be this infinite variability. So these conditions enabled by computation are what allowed for the overlay of Cartesian and topological models, so that a fully fluid spatial form, like FOA's Yokohama Port Terminal project, and this is the sections of the project sort of orthogonal, laid down like an orthogonal axonometric in plan, could now be described by changes in the serial section, which became the building's structure. These are the different sections, and we think of the section now as a descriptive rather than a projective device, right? First, we model the form, then we slice it, in any number of ways, rather than starting with a section and projecting it in space. And this is exactly the same logic, of course, that's applied to Studio Gang's Aqua Tower, except that it employs the serial iteration of the plan, defined as the changing profile of the concrete floor plate rather than the section. Now, if the first generation of serial projects animated architecture through formal variation, the next generation, within the context of full-scale 3D printing or additive manufacturing, shifts towards not just the variability of form, but the variability of material by adjusting the path, the rhythm, and speed of material extrusion in additive manufacturing to exploit, for example, this was the strand table by Matsis, by Andrew Kudless. And you can see in the close-up, there's a kind of micro looping of the bioplastic that is just by slowing down the speed, right? So that while it is curing, it eventually hardens, but it first sort of slumps. Or the natural slumping of concrete in the making of the columns of the concrete choreography. This was at the ETH, which exposes the serial layering of the 3D printing, but instead of trying to hide it now, right, is trying to expose it as material texture. We also see this in the 3D printed mud of the Casa Cavita and the Mud Frontiers by Ron Rael and Virginia Sanfratello. They have expanded what was once a modeling strategy into full-scale applications for rethinking the making of architecture, but in environmentally conscious ways. The last three sections of the book, in some ways, emphasize the sort of shift toward animate, material, and biotic models and their link to computation. We start with woven meshes, and we see the rise of complex woven systems that displace the gridded frames of modern architecture with complex meshworks. And they find their analogs both in sort of nature's rhizomes on the one hand and technologically networked culture on the other. Now, woven structural systems function through interlocking, the intertwining and entangling and knotting of strands that would by themselves lack stability or rigidity. And in architecture, trusses, lattices, geodetics have always operated by distributing forces like the woven strands of a basket or a fabric according to the geometry of the weave, which was evident in the early structural applications and explorations of people like Pier Luigi Nervi, who used a waffle slab system to both follow and direct the geometry of material forces. In contrast, current woven structural systems like Herzog and Demeron's Beijing National Stadium, that was also known as the Bird's Nest, which was where the structure was done by Arup, they intentionally misalign the true functioning of the assembly in relation to its perception, trying to undermine our expectations for a stable and ordered tectonic as a kind of nod to the true complexity of nature's material systems, right? The structure you can see in the sort of 3 diagrams that were, or models by Arup, you know, the actual structure is a fairly logical structure that then has an overlay of other strands, and then they get conflated into one plane through the tubular system, so that you also don't see this as the wrapping, you see it as one thing. And this is a strategy that Toyo Ito also uses in his Serpentine Pavilion. And in this project, he drew a box, then, you know, with openings in the box, and then a series of lines, you know, over the box, and then handed it to Arup and said, you know, make a structure out of this. So they start with something that was totally heterogeneous, and Arup develops a process, a logical process based on fractals, a process of progressive differentiation that, starting from this complex crisscross mesh, is then rationalized through a fractal system whose geometry then gets folded down on the sides of the volume. So, you know, in some ways, this is the logic, right, of the process. It's about thirds, right, this sort of rotating fractal, but then they extend the lines, you know, to produce this, fold them down over the sides of the walls, and then, you know, if that wasn't complex enough, then they alternate what becomes solid and void in the making of the structure, so that the structure itself, which has a logic, is sort of hidden behind. And here you see actually how the structure of the pavilion works. And it's about contesting the assumption that structural integrity is necessarily conjoined with the perception of a clearly ordered system, right? The form follows function doctrine of modernism. This is an inverting that as a logic. We then looked at the application of weaving to space through topological continuity of tubular structures like those that you find in Toyo Ito's Taichung Opera House, or the very many, which is Mark Forens's tubular networks, where here it's not a single strand, but a tube that becomes a kind of topological whole. And the work of Achim Menges, and also Hassan was part of this project with the Institute for Computational Design at Stuttgart, on the one hand, and Neri Oxman and her Mediated Matters group at MIT, they start their research on woven systems by studying the fibrous composites of the biological world. They look at cellulose in plants, collagen in animals, silk in the woven webs of spiders and silkworms, and chitin in insects and crustaceans. This project was based on looking at the chitin in relation to the fibrous exoskeleton of a lobster, recognizing that the heterogeneity of stranded systems in nature is critical to their functioning. And here a robotic fabrication method is used to weave glass and carbon fiber reinforced polymers, these strands that were dipped and then woven over a structure for the research pavilion. Now, Neri Oxman and her Mediated Matter group developed these silk pavilions. And on the other hand, these aren't just informed by natural systems, but also incorporates them as co-producers, where they brought in 6,500 live silkworms that are literally employed as biological printers, right? Think, you know, to construct these large architecturally spun silk cocoons, for those of you who are interested in multi-species kinships, you know. This is a co-produced design project. One of the most dominant shifts in the last 20 years has been also the move from an emphasis on form to an emphasis on matter, coinciding with the intersection of computation or computational technologies with material, environmental, and biological systems. Modernism, we say, subscribed to the principles of what we call the hylomorphic model, that matter is essentially formless, and it is the overlay of geometry that provides its formal definition and structure, so that the architectural forms produced would always be unrelated to the matter that fills them, right? You first design, you make your computer model, and then you pick a material, just like an aesthetic surface, right, to fill it with, as opposed to starting with the logic of matter. Now, contemporary processes that exploit the potential of material systems follow an entirely different route. They follow the experimental evolutionary trajectory of people like Gaudi, of Heinz Eisler, of Frei Otto, of Felix Candela, and others who always started with material systems as the basis of making form. And we see this evolution in projects like this. This is Maximilian Schell by Ball-Noches that investigates the deployment of a minimal membrane surface that gets hung, but it's aggregated. And it's based on the notion that matter already has its own capacity for self-expression and self-organization. Catenary systems is the one that we know the best through people like Gaudi, who started with these inverted hanging chain models, right? The hanging chain that then gets frozen and flipped over, where the geometric shape of the curvature of the hanging chain is a direct expression of the material forces in the system, right? Gravity and the chain. And the incorporation of digital design tools, people like Axel Killian, who developed catenary, that would simulate the physics of a membrane system. So he was creating a tool for architects to use that would be intuitive. And this enabled a kind of next generation of catenary structures. This is a project called Feathered Edge. It's made up entirely of just hanging colored string, also by Ball-Noches. Or other spatial and material explorations like the self-forming knitted textiles of Sean Alquist. And one of my favorite projects, or let's say one of the most compelling examples of emergent material behaviors, this was a series that Andrew did known as P-Wall, that follows the experimental tradition of Miguel Fisac, that tries to reconceive the planarity of a typical architectural surface. So each wall is composed, and many of these projects could fit into multiple categories of the book, and we decided, because this is also, a modular system, it's also tessellated, et cetera. But here, each wall is composed of a tessellated pattern of cast tiles generated by pouring plaster, and in later versions, he experimented with concrete, into modular fixed forms. So it was a wooden frame, hexagon, with lycra spandex fabric stretched across, and dowels positioned underneath. And the position of the dowels was generated based on a digital image. And these were vertically oriented dowels. And you can see this sort of from the process. That's an image at the bottom of it underneath. And then pouring plaster in, which is curing as the thing is sort of sinking, right? So there's the time of its curing, and at some moment it hardens and stops based on the weight and the different distribution of the liquid, right? So it's about the properties of matter that's producing the form, and the surface in the end becomes an index of these interacting material forces and constraints rather than producing an imposed geometry. Now, the lineage of Otto and Candela is perhaps best exemplified in the full-scale experimental projects by Philippe Bloch at the ETH and his research group, the Bloch Research Group, where, for example, he takes Frei Otto's cable net structure, the tensile structure, and Candela's shells, which find their progeny in this project that's called Knit Candela, which is a free-form concrete shell constructed using a suspended cable knit system and fabric formwork, and they left the fabric formwork on the project in the end. But the formwork is what shaped and molded the cell, right, in space by how it was hung. And they literally, Philippe told me, they literally packed the fabric formwork up in a suitcase and flew to Mexico City, and then, put up and built the project. Now, one of the most important contributions has also been the development of interactive, computationally driven form-finding tools that produce geometric visualizations for architects, so that the aligning of the tools with our intuitive sort of formal and spatial design processes become more direct. And the use of these tools in concert with material explorations was evident in one of my favorite projects of all time, which is the Armadillo Vault that was built at the Venice Biennale in 2016, also by Philippe Bloch. And the structure of this project is a free-form, doubly curved vault made of mortar-free. Get that? Mortar-free, right? There's nothing gluing the pieces together. It's dry assembled, discrete pieces of stone with a thickness proportional to less than 1/2 that of an eggshell, like at this scale. And it's an explicit material manifestation of the potential of geometry when linked with the intrinsic capacity of matter to self-organize through the alignment of form and force, to expose what we call endogenous matter-based architecture might become. The last section I'm going to show you is called multi-agent networks. And in a way, we stopped the book pre-AI, but you could see this as sort of the precursor to this. The last section, which is on multi-agent networks, which like swarms and crowds are intelligent, decentralized systems that are always composed of discrete elements, each of which operates like an independent actor within a kind of larger dynamic collective. And within the design disciplines, swarm behaviors, initially evolving from computer simulations of swarming, schooling, flocking activities of insects, fish, bird migrations. How many of us aren't always, wild when we see like swallows, like, like how did they do that, right? Who's leading that group? So these have become models for us for rethinking architecture and urbanism as a kind of dynamic multi-agent system. What is a city but a dynamic multi-agent system? Now here, the complexity of their global patterns emerge always from a series of local interactive rules. Now I divided this section into sort of 3 different categories because they've produced a wide range of practices, and these are very different. The first I called multi-agent matters, which sort of applies swarm logic to the making of architecture, almost like the making of a termite mound, right? As all the termites are moving, right? They're excreting this substance that eventually becomes the house that they live in. And of course, that was sort of the inspiration for Francois Roche, like Neri Oxman. He loves animals and insects and other things that become part of his process, about sort of making a project over time as a conceptual project. What would happen if the people who lived somewhere actually by their desires would construct, their own sort of termite mound. It was also a process in a different way used by Alyssa Andrzejczyk, who created this project called Cloud Pergola, or Mathematized Cloud. And it was based initially, she brings 3 different processes together. Swarming vectors that produce a kind of meteorological storm, right? That gets then frozen in space. It's translated into a gridded voxel lattice, right? So I now grid the entire space, and then is fabricated using a single but continuous robotically extruded thermoplastic filament. And the project also was exhibited at the Venice Biennale. It was, one of my top picks of that year, so I had to include that, but incredible, incredible project. The second group of multi-agent networks refers to larger systems applied to urbanism that focus on the collective emergence and behavior of populations, vehicular infrastructures, building clusters, or territorial elements whose interaction is always determined by algorithms calibrated to environmental influences. Some of the best work of this came out of the Parametric Urbanism research group at the AA in London, and people like Tom Verebes, who this was work in one of his studios. And this can instigate a range of what we say is potential settlement scenarios, or develop optimized systems of distribution. Like this was using it to develop a kind of branching network. Think of how we make streets or paths, right? That establishes a kind of infrastructural connectivity or the cellular allocation of building plots. The third group in this series are what often come under interactive and responsive systems. They are those that are made up of a field or fields of components that locally respond to the changing dynamics of the populations with which they interact. This is White Noise, White Light by Howler and Yoon that was built at the base of the Acropolis in Greece. It was a field of flexible stalks that light up, bend, rotate, and vibrate in relation to the movement of bodies that walk through them, like walking through a field, and the sound as people inhabit the space. And in two projects by Future Forms, Cirriform and Light Swarm, which capture sounds from the city through these sound sensing spiders and distribute that sound across the facade as the components themselves sort of light up and also rotate to underscore the swarm's movement. This was also the strategy that we used in one of our projects. This is a project that I did with Mona El-Kafif and Stephen Bates in Toronto. It was also here for a bit down in the Nog, and it transcodes sensory data that was collected using sound sensors that we located along 5 primary east-west urban corridors in Toronto, which then got transcoded into a streaming flow of rhythmic syncopated bands of pulsing light, what we consider to be the city's sort of collective heartbeat that moved across the piece. And that was then also reflected, this was built at the Gardner Museum in Toronto, and was reflected back to the city as a kind of interactive facade. In the case of other projects, it doesn't have to be populations or sound. This is Hygroscope by Achim Menges, and the one on the right is Oculus by Dosu in LA. It's not the movement of populations or sound that activates the piece, but the change in atmospheric conditions. So in the first one, in Achim Menges's, the Hygroscope project, it was humidity, the humidity on the streets in Paris. And literally, the project in both cases, it's the material itself that is moving. It's not computationally controlled. In Oculus, it is the heat that is heating up, and when it heats up, the oculi close, right? Because the metal actually changes its position based on the movement of the sun. And although from the perspective of architecture and urbanism, much of this research is still in its infancy in relation to what we could say is the complexity of biotic social and ecological systems that it hopes to emulate, the vast range of scales and potential applications of responsive systems or multi-agent networks indicate the many territories within which this research is kind of unfolding. So to close today, we could say that if within the industrial paradigm of the early 20th century, the intent of an automated process was to capture, frame, and functionalize time and space through repetition to make us more efficient, right? To make industry and capital more money, right? The diversity that we see that characterizes the complexity of these works at the end of the 20th century onward, in fact, does exactly the opposite. These become, in a way, I would say, a reaffirmation of life in their capacity for improvisation and evolution, and the seemingly limitless range of possibilities through which these get expressed. And I would say, as a kind of final note, for me, these are perhaps arguments for experimentation that operates in direct relation to the real, acknowledging not only the capacity of computation that's brought into relation with the complexity of form on the one hand and the thickness of matter, but also the role of the physical and the material as critical sites of invention from which new architectural systems, logics, models, and perceptions might arise. That's my call out to the Fab Lab, and that's it. Thank you.